Hello, everyone. Thanks for joining us for CNEN's second annual virtual symposium on advances in drug discovery and development. I'm Jeff Huber, Associate Editor at Chemical and Engineering News, and I'm delighted to introduce our next speaker, who is Sean Ekins. Sean is a pharmacologist and expert in the field of ADME tox, computational toxicology, and cheminformatics. And he will be presenting today on a talk entitled Open Science for Rare and Neglected Diseases. I'll be back to moderate a Q&A session immediately following Sean's presentation. We welcome your questions at any time. Just click the green Q&A button in the left corner of your screen. And if you need any technical assistance during the presentation, please click on the support button located at the top right of your screen. Please note that CNEN does not endorse any companies, products, or services that may be mentioned in this presentation. Finally, this talk will be archived and available on demand at the conference website for 3 months after the live broadcast until December 16th of this year. And with that, I'm delighted to hand things over to Sean.
Thank you very much, Jeff. Thank you very much, Jeff. I appreciate the invitation to talk today. I'd like to thank the organizers for the opportunity to present. I'm going to present on open science for rare and neglected diseases. Don't worry, I'm not going to pressure you to do open science, but I would like to ask you to imagine a time in the past you may have published your work openly along perhaps with the data. Or imagine a time in the future when you might be able to do this. The examples I'll outline today hopefully will try to strike a balance between both open and closed science. I'll try to show examples which demonstrate how open data can be used to describe how it can be useful for both neglected and rare disease research, and hopefully try to aid in increasing success. Ultimately, my goal will be to try to inspire you to take some of these approaches in your own research. I'm going to demonstrate how open data can be used to generate models and how this can then potentially lead to new leads. I'll describe my experiences working on rare and neglected diseases, and I'll potentially suggest what could be done to increase success in bringing ideas to the clinic. My focus will be on neglected and rare diseases where there's relatively less money invested and where the impact can be quite large. Diseases like tuberculosis at one end, which affect billions of people and kill millions every year. And on the other end, rare diseases like Sanfilippo syndrome, which potentially affect hundreds of people and are fatal, ultimately. We need to somehow address research and development on both sides of the scale. It's important also to think how and where we do science has changed over the centuries. The notion of a lab has really shifted so that we can pretty much do research purely on a computer or even a mobile device nowadays, perhaps even with global collaborators. It's even reached the point where the way we think of scientists has changed. Even my 5-year-old considers I'm not a scientist because I don't have a lab. So just thinking about how science and how we do research in the future, I think is obviously going to be quite important. Some of the things that I'm going to show today primarily use computational approaches. And I obviously don't have my own lab, so I'm pretty much dependent on a network of collaborators to do the actual verification. How we fund science has also started to change, as illustrated by neglected disease researchers who are now looking to crowdsourcing to fund research, or at least part of the research. Some examples here include funding of tropical diseases as well as tuberculosis. A group at the University of Maryland actually raised about $5,000 to fund some student research. Rare disease families are also looking to use crowdfunding to fund research. Some good examples here include Sanfilippo syndrome, which has raised over $2 million in the last couple of years, either through using heartfelt videos, in the case of the Saving Eliza, or using a celebrity to try to raise funds via doing very long distance runs. Obviously, another example from last year includes the ALS Ice Bucket Challenge, which was very successful, raising millions of dollars in money for this rare disease. Other families are increasingly looking to start companies to try to access NIH funding. And I recently described how anyone can pretty much start a rare disease company on a blog for rare disease reports. I'd like to inspire you to think how you could do drug discovery pretty much on a shoestring, with just an idea, some data, some tools, and a little bit of time. This slide just tries to illustrate that and break it down into essentially what you need to do. First, obviously, a good idea of what disease or target you'd like to work on. Potentially then find what data is out there that you can use and the quality of that data. And then bring it together with some tools, potentially even computational or in vitro tools that you have access through, either yourself or through collaborators. And then the final component being time. You need to think how you can fit that in alongside your day job, if it isn't actually your job. Ultimately, then, the potential is that you can come up with some ideas that will aid drug discovery. Probably the key starting point here is the idea or inspiration behind what you do. And this can obviously be driven by personal circumstance. Perhaps either you or a family member has a disease, you meet someone and they potentially inspire you, or you're driven by the surroundings you're in. Perhaps you're in an area maybe where the disease is endemic. It may even nowadays be something you read or hear, even something on Twitter that motivates you to get involved and do some research. Perhaps also it could be none of the above. There are obviously over 7,000 rare diseases, so you could just at random pick one. In the past, accessing data and tools was obviously quite limited to those in the drug discovery industry. And just to highlight the chemistry and biology desert, as I've coined it here, around the 2000s, there was limited ADME-tox data that was out there. There was a paucity, pretty much very little structure activity data. And the data sets that were available for modeling were very small. So essentially at that time, drug companies were the gatekeepers for most of the information on drug discovery. Now we're obviously in a different situation. The landscape has changed quite remarkably in just the last few years. We have many databases that are out there, both for chemistry and biology data, databases like ChEMBL, obviously, PubChem, open resources, journals that are all putting data out into the public domain that can be potentially used, as well as obviously computational tools that are now more accessible. So what I'm going to do is to provide several examples which use open or free data to create new intellectual property. And the three examples include tuberculosis, Chagas disease, and Ebola virus research. All of these make use of machine learning models. And what I hope to do also is to demonstrate the importance of collaborations through this work. As illustrated earlier, TB is still a global killer, and yet we rely on old drugs that were pretty much discovered 50, 60 or so years ago. Ultimately, we're losing the battle against drug resistance, so it's pretty important that we try to come up with some new molecules. There have been, however, considerable efforts in terms of high throughput screens, predominantly whole cell screens, that have been funded either by the NIH or through other organizations like the Bill and Melinda Gates Foundation. Several of these screens have put large amounts of data into the public domain. The NIH screens with the Southern Research Institute have put over 350,000 molecules out there into public databases. About 1,500 or so of these are active and non-toxic. Drug companies such as GSK and Novartis have screened their libraries of millions of compounds and put hundreds of compounds that are active into the public domain. And obviously other institutes are doing similar. So we can actually leverage this data to build computational models. And we've used the NIH data predominantly to build these models and then validate them with additional data, either molecules from other data sets or new molecules that we've selected out of libraries of compounds and then tested them in vitro. And generally what we see is a pretty high hit rate, in most cases over 20% hit rate, which is much higher than you'd expect from random screening, which is normally in the low single digits, if not below. In one example, with Joel Freundlich at Rutgers, we've taken the approach of virtually screening 13,500 compounds from the GSK antimalarial hit library that were published several years ago with one of our TB models, and used the model to prioritize the compounds. Once the molecules were prioritized, Joel selected a number of them, actually 7 compounds, and tested them in vitro. And 5 of those 7 were found to have activity against TB in whole cells. You can see here the most active compound is this triazine compound. One of these compounds, the triazine, was taken further. We did more potency testing and looked at selectivity. Ultimately, we found that although this compound was very active in vitro, it was ultimately inactive in the mouse. And we think this is due to solubility issues. Regardless, the computational approach was considered important enough to be part of a $26 million Center grant awarded to Rutgers about a year and a half ago. And the triazine series now continues to be explored there as part of this project that's looking at discovery for escape pathogens, including tuberculosis. So obviously the triazine series still continues to be worked on, and our efforts there are really focused on improving the solubility and showing ultimately that we can obtain in vivo efficacy. The second disease I'm going to describe is our work on Chagas disease. This is in collaboration with UC San Diego and Jim McKerrow's group. Chagas disease affects about 7 to 8 million people worldwide, and it's essentially a parasitic disease, where the parasite is called Trypanosoma cruzi. It causes disease. It basically affects the heart, and it's a chronic disease. The disease is curable, but there are very few treatments that are actually accessible, and there are no FDA-approved drugs. Sadly, the pipeline also for compounds is very sparse, so there's certainly a need for new treatments here that are less toxic than those that are available currently. Several groups, including our collaborators at UCSD, have developed high-content screens, and these have led to the development of several public data sets of compounds that have been screened against T. cruzi in vitro, and these can be used for computational modeling. One of these data sets from the Broad Institute was used to build machine learning models. The data set here essentially is dose-response data containing approximately 4,000 molecules. And we've used EC50 data from this, as well as cytotoxicity data, and a very small set of molecular descriptors, including FCFP6 fingerprints, as well as ADME type, very interpretable molecular descriptors. We performed leave-out cross-validation, both 5-fold and 50% times 100-fold cross-validation. And these models appear to be statistically meaningful, as we see 5-fold cross-validation values that are ROC values, which are greater than 0.8, where ROC is the receiver-operator characteristic. We also see pretty good sensitivity, specificity, and concordance with these models, whether we just focus on dose response or if we focus on dose response and cytotoxicity for the data set. Using the more exhaustive leave-out 50% 100-fold cross-validation, we also see ROC values that are quite similar, and concordance and specificity values that are relatively similar, and the sensitivity value just drops off a little bit to 65%. But generally, these models look quite useful for virtual screening. We're also able to identify the molecular features that are important in active and inactive compounds against this particular parasite. And we're able to show that tertiary amines and piperidines appear to be important for activity, while cyclic hydrazines and electron-poor chlorinated aromatics appear undesirable. The models were ultimately used to score small vendor libraries of drugs, drug-like compounds, and natural products to try to identify new molecules for testing. We narrowed down approximately 7,500 compounds to 99 molecules that were purchased and tested in vitro. And out of 99 compounds that were tested, 11 had EC50 values that were less than 10 micromolar, and 5 of these were submicromolar in vitro. Ultimately, we tested these 5 compounds, including verapamil, pyranidine, furazolidine, tetranidine, and nitrofuril. We tested these obviously in the in vivo model, and the in vivo model is a mouse with a T. Cruzi strain which expresses the firefly luciferase. And this enables us to use luminescence detection in vivo so that we can easily identify which compounds are more efficacious in the short-term model. As you can see, the vehicle shows this fluorescence where the parasite is localized in the body, in the bottom image. And the most interesting compound from our perspective was pyranidine, which showed almost complete clearance of the parasite from the mouse. And this data is visualized also on the bar chart on the left-hand side, showing the statistically significant difference with a number of these treatments in vivo. The most interesting compound from our perspective that was identified was the pyranidine. This is already an approved drug in Europe for malaria in combination with artesunate. So this presents really a very useful starting point for further studies to try to identify whether the compound is actually active in a more longer-based study, more of a chronic type treatment. There's very little in terms of information around this compound with known activities other than against Plasmodium falciparum. More recently, it's been shown to be active against a number of parasites, Babesia and Theileria, but that's pretty much it. So this really is an interesting opportunity that we're pursuing in terms of trying to use it as a starting point for submitting further additional small business grants. The third example that I'm going to describe now is my work on the Ebola virus outbreak. And obviously, last year there was a great deal of interest in this, and now it appears to have slowed down a little bit, although there are still occasional outbreaks in Africa. Obviously, there is no approved treatment, even though occasionally we hear news about a vaccine or new molecules that are being looked at. There's still nothing, to my knowledge, that's been approved. So I think it's still quite important that we try to find molecules that can be used in the clinic. And about a year ago, I got involved in this, trying to look at compounds that had been published from various in vitro screens that had been done in the preceding couple of years. And I came across a study from a group at Stanford Research International led by Peter Madrid and colleagues. And they had identified from a high throughput screen a number of antimalarial compounds, including amidiaquin and chloroquine, that appeared to have micromolar activity against the Ebola virus in a number of different in vitro systems. A second study from another group identified a number of selective estrogen receptor modulators. And I wondered at that time if these compounds, which were really probably the most promising in vitro hits at that time, potentially shared a common pharmacophore and maybe were acting on a similar target. So using a computational pharmacophore approach, I showed that they appeared to fit the same model composed of multiple hydrophobic features, which are shown here in blue, as well as a hydrogen bond acceptor, which is shown in green. The pharmacophore was also used to screen several databases and propose compounds for testing. With a little bit more literature searching, I came across a target protein from the Ebola virus called VP35. And this particular target appears to contribute to viral escape from the host innate immunity and is required for virulence. And my interest around this particular protein got me thinking about, well, maybe this was the potential target for these compounds. So I explored this target in a little bit more detail. And so I took a second approach, which was to look at all the crystal structures with ligands for this VP35 and built common feature pharmacophores around the crystal structures and the ligands. And generally what I saw was the commonality between the pharmacophore features consisting of multiple hydrophobic features and additionally hydrogen bond acceptor features. So there was a great deal of overlap here between the ligand-based pharmacophore and the structure-based pharmacophore. I also took a third approach, which was docking molecules, and then in this case, obviously, antimalarials and SERMs, into the protein. And we can see here on this slide a number of these molecules docked into the protein, and the scores seem to be quite favorable. A final approach I took was working with the data that Peter Madrid and his group at SRI had actually used from the high throughput screen. And so I took the 868 molecules with the viral pseudotype entry assay and Ebola replication data and used this to build machine learning models using the same descriptors that we used in the Chagas models previously and the TB models. And we looked at compounds that were active as being less than 50 micromolar, and the rest were classed as inactive. And in this particular case, I looked at various machine learning approaches, including support vector machine, as well as recursive partitioning, forest, and single tree approaches. And all of these models were validated using leave-out groups. The analysis of this data seemed to show that the Bayesian models appear to be consistently the best in terms of the 5-fold cross-validation, as well as the more exhaustive leave-out 50%, 100-fold cross-validation. The receiver-operator characteristic curve data here is obviously in excess of 0.8, so these appeared quite useful. And the features that appear to be good for actives, both in the pseudotype assay and the replication assay, appear to be piperazines and phenothiazines, which are tertiary amines, while the bad features appear to be secondary amides and carboxylic acids. So potentially these were features that were important for targeting actual activity against the Ebola virus. So we use these models to go through the Microsource Spectrum library of a couple of thousand compounds, and this represents drugs and drug-like compounds. And out of the library, 3 molecules were scored quite well and were not in the training sets for either of these models. The 3 compounds were tested, and obviously we did the analysis in the laboratory with Robert Davey, the Southwest Research Institute in Texas. And the compounds were purchased by Peter Madrid at SRI. And these 3 compounds were found to have EC50 values between 200 to 500 nanomolar and represent much more active compounds than the chloroquine, which had an EC50 from about 7 to 10 micromolar. So these compounds also represent molecules that have reached clinical trials for other diseases. So they appear to be quite promising. The 3 compounds also map quite well to the pharmacophore that was generated from the antimalarials and the SERMs described earlier. So it's possible that they could also be hitting the same or a similar target in the Ebola virus. This work is still in progress, and we're still looking at which compounds we put forward into a mouse model. But we've shown quite nicely through all of this work how we can use public data to try to propose targets for compounds that have been identified through whole cell screens. And we can also show how using the data from the screens generated 2 years ago can actually be used to find new compounds that are clinically accessible. And this approach is obviously quite extensible to other targets. There are a number of data sets that have been published quite recently. We've collated molecules from the literature and shown there are about 55 molecules that have activity against TB. And then a couple of more recent reviews have shown additional 60 compounds from a review in Drug Discovery Today, and a further 53 compounds and 80 hits respectively from 2 additional papers appearing within the last few months. So there's certainly well over 200 compounds that have shown activity against Ebola. Obviously the key here is to get compounds that can be used and are active in vivo. And we've made the models available and they're accessible through this particular link, which I'm going to describe a little bit more about over the next few slides. So this brings us to how can we make models more accessible alongside data. Much of the previous slides has focused on accessing open or free data to build models where we can try to create new IP. But most of the time we find computational models reside in papers, but they're not actually all that accessible for other people. So this is obviously undesirable. So how can we make them more accessible? There are now obviously a number of resources for ADME and tox modeling that are out there, which I've just highlighted on this slide. So there is certainly more interest in sharing data sets and models around the ADME and the tox space. In recent work with Alex Clark, we've made some of the extended connectivity fingerprints and the FCFP6 fingerprints more open and accessible alongside Bayesian algorithms. So now we basically have these available in open source so that anyone can use them and create tools with them and build models that are open and accessible and potentially shareable. And we published this work last year and more recently in 2 additional papers that I'm just going to briefly overview. Now that these descriptors and algorithms are open, we've actually used them for building computational models that have been implemented in mobile apps like TB Mobile. And this slide shows a receiver operator curve for a model based on INHA data, as well as other compounds that are not INHA targeting compounds that we've collated. And you can see how the algorithm's able to differentiate the actives from the inactive compounds. Now, if we scale this up and look at the additional targets that we've looked at within TB Mobile, we have Bayesian models for most of the targets in this software, so that we can essentially profile new molecules and predict the likelihood that a compound is going to be a target, is going to target a particular protein within TB. This is likely the first example of machine learning algorithms being used within a mobile app that's used for scientific research. And TB Mobile is obviously freely available and is available for an iOS system. And we've published on this over the last couple of years, so I'd refer you to these papers to find out more about this particular software and how we've used the Bayesian approach with it. We've also implemented the same descriptors and algorithms in a commercial implementation of CDD models. And this is basically software where you have your own private vault of data. So now the user can build their own models within the vault, generate the ROC curves that are shown here on this slide. And in addition, we've enabled the user the ability to export the models from the software so they can be used elsewhere in other technologies that the user may have, either developed themselves or commercially available. And one of these places is obviously accessing the models in mobile apps. And another mobile app from Alex Clark is the freely available MMDS, which is essentially a spreadsheet functionality software. But now this can read the models that are exported from CDD or from elsewhere, and the software is able to highlight the atoms that are contributing to the activity, as well as score the molecules based on the Bayesian models that you integrate into the software. I mentioned at the beginning how data is becoming more accessible. And one of these sources I listed was the ChEMBL dataset. This has now been used by Alex to build thousands of models for different proteins as well as whole cell screen datasets. This was achieved by converting the data automatically to negative log, removing duplicates, and selecting cutoffs for activity, so building just binary models initially. And these models balance both the active and the inactives, as well as the structural diversity distribution. Ultimately, over 2,000 models were developed from ChEMBL 20. And we skipped targets where the data sets were very large or where there were very few measurements, less than 100 measurements. So what do 2,000 or so models look like? These two plots show the average ROCs against the folding bit size. And in general, what we see is the models on average have ROCs that are greater than 0.75 or over 0.8. And these suggest that the models are likely to be very useful. We've even made them accessible on a website that's listed on this slide at the bottom, and described the research more recently in a couple of open papers. These models are obviously quite useful for doing drug discovery research. In addition, you can obviously build models yourself, and one example is that I'm particularly interested in is modeling drug transporters. And some of the key transporters that I've been working on over the years are shown on this slide. And more recently, we focused on transporters like MATE, NTCP, ASBT, OCTN, etc., both uptake and efflux transporters that were of particular interest. Several of these models we've published in a recent paper in Drug Metabolism and Disposition, using either data from our own studies or from the literature. And we've used the open descriptors as well as commercial descriptors to show that essentially we're getting very similar models, both with leave-out statistics. And these models can obviously be exported from tools like CDD so that we can put them into mobile apps and then use them for profiling different new molecules, for example, compounds that we're interested in testing in vitro. So just by drawing in the structure in the mobile app, we can score the compound against the various Bayesian models that we've got integrated. So you could imagine building your own models of interest and uploading them into the mobile app, and then scoring compounds that you want to potentially purchase. So I think the availability of such data and models and tools certainly presents us with an unprecedented opportunity, both for neglected and rare diseases, where obviously we need to do R&D on a shoestring. This is particularly important when you consider that the NIH budget for rare diseases is less than $1 billion, at least for the ORDR in 2015. So for some of these diseases, they're relatively easy to treat. And obviously, there are certainly now more data sets that are out there that could be applicable to trying to find compounds related to some of the diseases. The advantages, obviously, of rare diseases in particular is that only quite small clinical trials are possible. And there are some new incentives that we should be aware of as scientists. One of these is obviously how we can see some return on investment. And a particular area, both relevant for tropical diseases and rare diseases, is the Tropical Disease and Rare Pediatric Disease Priority Review Voucher Program. What I've listed here is the golden ticket. And these essentially are awarded to companies that provide or have drugs approved by the FDA for tropical diseases or rare pediatric diseases. And these have a real monetary value in the order of hundreds of millions of dollars. And a good example here is the United Therapeutics sale of their voucher for $350 million to AbbVie recently. So although some of the diseases, the rare and neglected diseases, may have very small populations or have very limited markets, the potential to obtain one of these vouchers obviously brings a real return on investment. Of course, a lot of what I've described so far is doing virtual drug discovery with collaborators that obviously have labs that can do the testing, in many cases against diseases where you have to have quite stringent resources in terms of working with both infectious pathogens. So a lot of these things are not possible for most people, but you can start to do open science without actually having a lab, obviously. And one of these approaches is to use technologies that are already available to everyone. And there's many ways to do that. One is to even just tweet your ideas or observations when you're at a conference, potentially a scientific conference, such that the rest of the world gets to hear about what you're thinking or what may be being presented at that conference. And last year with Ethan Pilstein, we put out a little recommendation or 10 simple rules of how to live tweet at conferences. So your contribution to open science could be as little as tweeting at a conference, and that could then lead to additional collaborations. And in my own experience, several of the collaborations that I've been involved in have actually started with tweets. And the Ebola example represents a good example of that from my own experience. So some of those recommendations are obviously shown in that particular manuscript. I think also what we'll see in the future is that our lab notebooks will also change, so that we'll be essentially using mobile apps that cover diseases that we work on, and we'll be tracking the information that comes in as well as the open data that's available, both from our collaborators as well as from the rest of the field. Such tools already exist, and these are obviously accessible to non-scientists. And one example is a mobile app called Open Drug Discovery Teams, which Alex Clark and myself put out several years ago as a way to aggregate information from Twitter feeds as well as Google Alerts on both rare and neglected diseases. And this mobile app is able to handle chemistry information as well as other information that comes from both Twitter and Google. And these tweets were basically saved indefinitely, so you could look back through them. So the future, more of open science related to neglected and I think also rare diseases, is going to rely on how we can use some of the information that started to become more open and accessible alongside some of these new tools and technologies. In conclusion, I hope you can imagine how open data can potentially lead to new leads and IP for drug discovery, and how in a resource constrained environment like both rare and neglected diseases, this could be an idea worth sharing. I think virtually anyone can do this kind of research if you have the time and you have the access to some of these technologies. The data is obviously out there, and increasingly these tools are becoming out there in terms of technologies on mobile devices as well as on the desktop. From my own particular experience, these computational and experimental collaborations with open data have led to both new leads, new IP, and new grants for collaborators, as well as for the groups that I've been working with. Even in Ebola, we had enough data in 2014 to build models and suggest compounds to test, while the actual, the main interest in the disease was going on. So I think there's definitely an opportunity that we can be more responsive using some of the data that's available. We can certainly make our findings open and published as immediately as we can. And the work that we did on Ebola virus and the pharmacophores was initially published in F1000 Research very quickly. And even before we published the work, we made some of it available also on Figshare so that the data and the molecules were accessible. So I think there's also a huge opportunity to work on rare diseases, and but we still have to think about what challenges exist. Certainly sharing and accessing information and knowledge is a big one in terms of what we can share and what is private. Still, there's a lot of people that don't trust models that are created. And I think what we can see from developing models for thousands of these targets, as well as data sets in ChEMBL, is the validity potentially of using this type of approach. In the past, people have focused on potentially one model, whereas now we have access to thousands of models. I think another area we need to think about is that most people still think that you need supercomputers to do drug discovery, when actually maybe all you need is a mobile app. And you don't actually need millions of molecules to sort through. You could just look through pretty small data sets of hundreds, if not a few thousand compounds, and find things that may be relevant to you. So there are still maybe some barriers to sharing and collaboration, but from my experiences, I'd at least say that those barriers are surmountable. It just remains for me to acknowledge the various collaborators that have made this work possible, and specifically collaborators whose work that I've mentioned today include Alex Clark, Jair Lage de Siqueiro Neto from UCSD, Joel Freundlich from Rutgers, Peter Madrid from SRI, Robert Davey from Texas, and other collaborators including Megan Coffey, Ethan Perlstein, Robert Reynolds, Nadia Litterman, Chris Lipinski, Chris Southern, Tony Williams, Carolyn Talcott, Malabika Sarkar, Stephen Wright, Mike Pilastri, NEI, and Barry Buning and colleagues at CDD. I'd also like to thank BioVia for providing the software that was used in a lot of the earlier Bayesian model work and machine learning, and also the NIH that funded the TB and Chagas work. And with that, thank you.
Hey, great. Thanks so much, Sean. That was a great presentation. Before I end up asking some questions I just want to tell everybody that is listening to this presentation right now, you have the opportunity as well to ask questions of Sean. All you need to do is click the green Q&A button in the left-hand corner of your screen, and we'll be able to pose some questions to him. So Sean, one of the things I wanted to ask you was, when the topic of open science comes up, I end up thinking about negative results and how important negative results can be to developing new leads. Can you talk about your experience working with negative results, and if the landscape of using negative results is changing in any way for fighting rare diseases?
I'm sorry, Jeff, there was a lot of echo on your question. I think what you were asking was about the use of negative results. I think what I've seen, obviously through a lot of the data that's been put out there, has come from large wholesale screens. So there's obviously negative data as well as positive data, and that's important for building the machine learning models. What we've seen from some of the bigger screens from the drug companies is that they only put out the active compounds, which obviously is important, but you don't get the negative information as well. So that really hinders you in building models with their data, unless you're trying to build some sort of continuous structure-activity relationship, where you're going to see a range of activities, but you're not going to have those negative data. You may also be missing, obviously, various compounds that isn't obviously available in some of the data sets like the NIH libraries, where you've got all the information that's accessible, where you've got the negatives and the positives. So I think that's, from my experience, the TB side is definitely an example. Also from the malaria side, we used the 13,500 compounds that came out of the GSK screen of a few million compounds for malaria. Those were only the actives for malaria that were published. And in their example for TB, they screened a couple of million again, but put out 177 active compounds, which is still incredible that these companies are putting that data out there. But it just also shows that that's positive information. That's just actives and not inactives. So it's still very, very useful and very valuable. But in order to build kind of these machine learning type models, you need the negative data as well, which obviously these drug companies can do, but no one else can do that unless they make that data public.
Great, thanks, Sean. Let's see, there's a question that came in. Someone asked, I'm a computational chemist, and I would like to know how one can enter into cheminformatics.
I think the question was from someone that is a computational chemist and wants to know how to do cheminformatics. If I'm correct, I mean, I think that the two of them are obviously the same. It just, for me, it just seems that, yeah, I think they obviously are already probably doing cheminformatics and they just don't know about it. I think that there are obviously technologies that are out there that they can tap into nowadays that are available. As I mentioned during the presentation, there are even mobile apps that they can use to do cheminformatics. Some of the things that are available now as mobile apps, most people would think would only be accessible on the desktop. But I think, yeah, more and more there are these tools that are out there that pretty much anyone can use. I don't even think you need to be a computational chemist to use them. And that's really the point that I was trying to make, that you know, people even in the rare disease space that become sort of citizen scientists can use some of these technologies and do a lot of the work themselves. I mean, they may need to sort of connect to other people and collaborate with them, but I think some of these tools are relatively intuitive that they can be used.
Great. Another question that came in was, someone asked, was the pharmacophore of the various Chagas compounds studied computationally by the same method as the Ebola compounds?
So was the pharmacophore of the various Chagas compounds studied computationally by the same method as the Ebola compounds? Yes, I used the same technology within Discovery Studio to develop the models in both cases, and also for building the Bayesian models, I used Discovery Studio, and more recently we've obviously used the open Bayesian approach for building the machine learning models across Chagas as well as Ebola. And we see models that are very similar in terms of the ROC values. So yes.
Another question that came in, Sean, was how do you suggest curating data? For example, appropriate positive and negative controls, reproducibility?
That's a great question. Obviously, I haven't dealt with that so much here. I think part of what we rely on is the data that's uploaded as it is. I think, yeah, you have to have some idea of what the controls are. Sometimes that's in publications that goes along with the data that's archived, or it's in the protocol that's uploaded. Most cases, what I haven't done is curate data sets extensively. I think most of what I've been able to do is essentially just come up with cutoffs for what we'd consider activity, and that's mostly done with collaborators who have the screens themselves, so they have an idea, obviously, what's an active compound and what's not. So you pretty much rely on the collaborators in terms of the expertise around the in vitro assay. I'm not really advocating here that the curation side of it. Obviously, there's you have to rely pretty much that the quality of the data is there. And I've published several papers in the past about quality issues around some of the data sets for building models. Many cases, you're left pretty much to take it at face value, and obviously you use your, you know, working with collaborators. They obviously have a good feel for what's, you know, good results and what's bad results, and then obviously they've done some of that curation for you.
Sean, another question that came in was regarding your data mining process, and somebody said, did you experience any limitations when using your data mining approach?
In terms of data mining limitations, yeah, that's a good question in terms of hadn't really thought so much about what was the limiting factors around them. Obviously, you're really limited by the training sets. Some cases they can be quite small, but what we're seeing with some of these screens, though, is in the order of thousands of compounds, if not hundreds of thousands. The Chagas data set was several thousand. The Ebola virus was probably the smallest one at just under 1,000 compounds. The TB data sets were getting upwards of 350,000. So it can pretty much be the, you know, obviously the structures that have been screened, you know, coverage of chemical space, and then how you make predictions. Are you actually able to sort of jump scaffolds, come up with totally new scaffolds that haven't been found before? Some of the limitations we find is that we're discovering things that already have been discovered in the past, maybe 40 or something years ago, and they seem to be popping up. And that's not necessarily because they're represented in the training sets. I mean, that I think is probably one of the biggest limitations that I've seen, is that your ability to come up with new structures, and that's always a bit of a problem regardless of what technologies you're using. That's something we all struggle with, I think.
Sean, another question that came in, they asked about the drugs you described against the Ebola virus. How many of the drugs that tested against Ebola were natural products, and have you had to test natural products?
I looked at have been natural products. None of the compounds that we looked at through our own screen were natural products. So those 3 examples were not natural products that were active. The original screen, I think, were all drugs. And I think some of the more recent screens that have been published are all drugs as well. I mean, there's probably some natural product work that's been, some compounds that are natural products that have come out of other screens, but they're pretty limited, and they weren't used in the model building in this particular example.
Sean, another question that came in was someone mentioned that a few anti-malarial compounds are found to be active against the dengue virus. Do you think the target protein is the same?
Yeah, that's a good question. Do I think that the target is the same? I obviously haven't looked at that. I haven't looked at dengue virus. So no, I can't comment on that. I mean, it's possible, but I don't have any evidence for that.
Another question that came in was from someone who says they have a nephew with a mutation on the ABPR2 gene, but no structures have been published for the misfolded protein. What tools would you suggest for screening for an antagonist for misfolded proteins?
Yeah, very interesting question. This is an incredibly interesting question. I mean, it's almost getting to the point of trying to discover chaperones for the protein, I would guess. I think, obviously, what would probably need to be done here is maybe some homology modeling around the protein. And then, obviously, some docking. You would need to do some docking into that protein. And this is obviously a huge stretch because each of these approaches has issues with it in terms of the accuracy. If there's any way to get some screening done with a library of compounds against this particular target to see if you can get some sort of chaperone activity compounds, and then maybe use those as a starting point for a pharmacophore. That might be one way to go. I think that's possible. There are examples in the literature of people that have used computational approaches to go after chaperones. Yeah, I think that's a really good question.
And so that's all the time we have for this presentation. I want to thank everybody for all the great questions, and I want to thank Sean for his great presentation. There are going to be many more talks beginning at the top of the hour and throughout the day here for this symposium. You can find the full program on the agenda page and which is located at the upper right-hand side of your screen. In the meantime, please stop by the virtual exhibit hall and the lounge to check out our sponsors and exhibitors, or to network with other attendees. And be sure to join the conversation about the symposium on Twitter using the hashtag CENSIM, that's SYM15, CENSIM15. And with that, thank you so much for attending today.